So when you were looking at that element and that magnesium right here, and then it was 24.3 something. And then we were saying, well, you can use magnesium 24 is a natural, magnesium 25 is a natural isotope, and magnesium 26 is a natural isotope. And then we're saying, well, this is the one that number's closest to because that's the most abundant. So the question comes, like, why don't you just average these three? Why don't you do it? So let's use a real life example and figure this out. So why not just do normal average? Let's say you take this class. Your homework is 50%, your tests were 40, and your final was 10. Let's say that on homework they got 100, and on tests they got 100, but on the final they kind of like got all freaked out and they only got a 25. So if you average those numbers together and you make a 75 for the class, is that fair? Is that a good representative of their knowledge? And if you're saying no, it's probably because you recognize that the percentage that those two are, it's 90% of the grade is here. This final is only 10% of the grade. So when we calculate your grades, it's not just taking the average of all the numbers, but it's taking something called the weighted average. And it's the same thing. If you get a sample, it's mostly going to be magnesium 24, but it'll have a little magnesium 25 and a little magnesium 26, and that will affect the average weight of the sample. So what that means is, like, if you get a little handful out, or you get a big handful out, or if you get a trash can's worth out, you're still going to have mostly magnesium 24, but with a little bit of 25 and a little bit of 26. And this is really important. We keep going over it because we're going to be using this number for so many things. So here's another illustration. This has more than 100 dots, but imagine that there's just 100 dots. Imagine that 90 are purple, 9 are red, and 2 are, that's supposed to be green, and 2 are green. The purple dots weigh 20 AMU, and the red and the green are heavier. Is it correct to say that this sample will weigh 20 times the number of purple dots? Just so you know, it's not, because those other little dots, like this one is green and this one is green, they're a little heavier. They're going to mess up the weight and they're going to make it just a little heavier. And the 10 red dots that are in there, those are also going to make the sample just the tiniest bit heavier. So this would be an example of how we see some of the different compositions. This one is 90% neon 20. It's only 0.27 neon 21, and 10% is, 9% neon 22. So you would expect the mass for neon to be around 20. And look, this is what it is. It's around 20. It falls close to him because this guy is 90% of the mass. So how do we do the math for it? If you're a big formulas person, you take every isotope and the mass of every isotope, and then you multiply it times its percentage as a decimal. And you just add them up. But if you're not good with that equation, don't worry. It's not too hard to calculate these things. So the average atomic mass, take into consideration the weighted average of all the natural isotopes an element has. So predict and calculate the average atomic mass of this element. So it's got 3 isotopes, a light one, a heavy one, and a heaviest one. And this is, you kind of know the answer on this one going into it. So what we're going to do is we're going to take, when we multiply the mass times the decimal version of the percentage, we'll add it to this one's masses times the decimal and this one masses times the decimal. So I'm going to say that we take 19.99 times 90.92 over 100, and that's because it's a percentage. So that's the lightest isotope. We're going to add to it the second lightest isotope, which is the 20.99, plus the 0.26 over 100 times. And then the heaviest isotope, 21.99 times 8.82 over 100. You're just going to add all of those up together, and you will end up with this number when you do it. Let's make sure that that works. Whoops, let me make my calculator go away and come back on the screen. All right, so we're going to say 19.99 times, and if you want to do the math in your head and call it 9.9092, that's fine.
Legendary chicken with a legendary...
Haven't had the ads go out on this one. So we'll take the 19.99 times 90.92 divided by 100 plus 20.99 times 0.26 divided by 100 plus 21.99 times 8.82 times, or divide by 100. And when you add all that together, you get 20.169. If you're wondering about sig figs, or if you're stressing about them, we're adding, all the things we're adding are going to be going to 4 sig figs. And when you do these, it's a little funny because I know you're saying, oh, well, that's 2 sig figs right there. How that's going to change it. Most of the time when you do these, you're taking it to the same number as the isotope masses that you have. This is 20.17 AMU. Now go ahead and do this problem, and there's one more right here, the lithium problem. After you get done, we'll work those in class. These are the learning objectives. Make sure that you go through and you look through them and you understand these different topics from your notes. It's like a review that you can do on your own of the notes.